Okay, so I think good afternoon. I don't think I need to repeat from the last time. So we had introduced some basic notions about groups. Now I want to talk next about normal subgroups. So these are some special subgroups, and the idea is that a normal subgroup is a subgroup. So we know that if we have a subgroup of a group, we have the cosets, and so we could ask ourselves whether the cosets themselves form a group in the obvious way. And for this, it turns out we need a condition, and which is the one of normal subgroup. So if H sub G is a subgroup, so is or when is G mod H naturally a group? So naturally here obviously means we want that if we define AH times BH to be ABH, this should define a group. And if you think of it a moment, you can see there is a problem quite immediately because this is not even in general well defined. So it will depend on representatives. Let's see that. So we need product to be well defined. So not depending on representatives. So that means we should have that A, B, if this would make sense, we should have that ABH should be equal to A prime B prime H if AH is equal to A prime H and BH is equal to B prime H. So here we are just talking about the fact that it even makes sense to do this regardless of the group structure. Well, we can, for instance, if we take A, so take e.g. A just to be 1, and then other representative B to be H, general element of H, and B just, I can take B even equal to B prime, some element, general element of G. So what does the condition mean then? So then we have A is 1, so A times B is B times H, should be equal to A prime is H, and
A
is
prime.
what?
What is A prime? A is equals to 1, B is H.
So A prime. Sorry, it was a stupid misprint. Yeah, I mean obviously otherwise it makes no sense. So yeah, anyway, it's A prime. So these two are equivalent, and so and then we would have that. So then we need, so then we should have this, and so I can, so this means I multiply by b to the minus 1, we get h is equal to b to the minus 1, hb, h, that means b to the minus 1 hb is an element in H. So therefore we see that the condition for this product to be well defined is that for again, so this was B. I don't know why I'm confused. So if I can replace B and B to the minus 1, that for any element B or G in G and any element H in H, G, H, G to the minus 1 is in H. And so we take this as our definition. Subgroup H in G. Is a normal subgroup if, as I said, G, H, G to the minus 1 is an element in H for all H in H and all G in G. So there are some trivial cases of normal subgroups. For instance, if G is abelian, every subgroup is a normal subgroup. Then the trivial group just consisting of 1 and the whole of the group is a normal subgroup. For any G, and what else? Let's look at an example of a subgroup which is not normal. So we had one example of a non-commutative group which was S3. So in S3 we can look at the subgroup H, which is consists just of two elements, namely the identity and one which commutes the last two. So this is a subgroup because if you apply this twice, it's the identity. And I claim it's not normal. So for instance, I can conjugate it with another thing which commutes just two things, which was called transposition. So if I take 1, 2, 3, 2, 1, 3, I take just the non-trivial element here, 1, 2, 3, 1, 3, 2, and then I have to multiply with the inverse of this. But this thing has again the property that its square is equal to 1, so it's its own inverse, so I can write it itself. So 1, 2, 3, 2, 1, 3, and maybe I don't go through it. If I'm not mistaken, it's 1, 2, 3, 3, 2, 1. And so this does not apply in the subgroup, so we have an example of a non-normal subgroup. Okay, so it's a simple thing. Now, I had kind of promised that, so the motivation that I gave now for the definition of a normal subgroup is that the set of cosets in a natural way would form a group. now we have to want to show that this is actually true. So that if you have a normal subgroup, then you can get the factor group, which consists of the cosets. So proposition, definition. So let H and G be a normal subgroup. Group G, then G mod H with the obvious product AH times BH is equal to ABH is a group. And it's called the factor group of G by H. Maybe also quotient group. Anyway. Okay. So, in some sense, we more or less already did it, so we just do it again. So, the main point is that the product is well defined. So we take A prime, B prime, the elements in G, with the AH equal to A prime H, BH equal to A prime H, and now so that means we can say that A is equal to, so say A prime is equal to A times H1, and B prime is equal to A times H2. What? B times H2, yes. Again, a nice misprint. Where these are elements in H. So, if we take now A prime, B prime, this is therefore equal to A H1, B H2. Now we have to multiply in a nice way with 1, I expect. So, you can write this as A so we put here B to the minus 1, H1, B, H2. No, this is just multiplied by 1. But now we can see that this thing is a conjugation of B to the minus 1, H1. So this is an element in H. So this means this is an element in A, B, H. Because I can write this AB times whatever this thing we call H times H2. And so we see that the product is very and that this is that this defines a group. It is straightforward from the definitions of the fact that G itself is group. So the group actions of G mod H follow directly from those G, namely for instance for the associativity, if I take AH times BH times CH, this is equal to ABH times CH, this is equal to ABCH, and then you can move the other around. Now use here the associativity, so this is A times B, C, H, and then obviously you can go back and A times B, H times C. Okay, and the neutral element is H, and the inverse of A in H, in G, AH is A to the minus 1H, as you can see directly from the definitions. Okay, so this is a nice group. Let's look at them. So now I want to briefly talk about group homomorphisms. It's a standard thing in all of mathematics that if you have some nice structure, which usually means you have a set with some structure, you are interested in the maps which are compatible with the structure. So like for vector spaces you have linear maps, for topological spaces you have continuous maps and things like that, and usually these are the main tools for studying these objects. And so for groups, the only structure that we have is this multiplication, so the homomorphism will be a map which respects the multiplication, the map between groups. So definition. So if G and H are groups, the homomorphism P from G to H is a map from G to H, which is compatible with multiplication, so such that phi of A B is equal to phi of A times phi of B for all A in G. Obviously here we have the multiplication in G, here we have the multiplication in H. This is the compatibility. Now in principle, a group has a bit more structure, it has a neutral element, and every element has an inverse, but we'll see in a moment that from the homomorphism property it follows that the 1 is sent to the 1 and the inverse is sent to the inverse. So, but for a moment, let's look at some simple examples. For instance, if A is an integer, then we have the multiplication by k from z to z. So this is always z with the addition, which sends n to k times n. This is a group homomorphism. No, because obviously k times n plus m is equal to k times n plus k times m. And another one would be, you can look at, we have this map pi from, R, from the integers, so k is now say a positive integer, to what I called zk, which sends an integer to the rest when we divide by k. This is also group homomorphism because we know that if we take the rest of the sum, then this is the sum of the rest. If possible, we have to take the rest again, but that's okay. Oh, like okay. Okay, so I mean this is the sum of the rests is the sum in this group of the rests. So the rest of the sum is the sum inside here of the rest, which means the rest of taking after taking this. Okay, so this is these two examples. Now let's see what comes next. Yeah. So maybe I do not. So as I said this thing, we have this remark which I will not prove. I leave it as an exercise. If f from G to H is a homomorphism of groups, then f of 1 is equal to 1, and f of 8 minus 1 is equal to f of 8 minus 1. This follows directly from the definition. I think you can, it's one line. And so, obviously, if you have homomorphisms, which are some maps, you can try to compose them. The composition of homomorphisms will be homomorphism. And if such a homomorphism is bijective and has an inverse, then it's an isomorphism, and the groups will be called isomorphic, which means that for most means and purposes we can view them as the same group. So the composition of group homomorphisms is a group homomorphism. H, C, H, K are group homomorphisms. And it follows that psi equals to phi and G to K is a group homomorphism. And this follows directly from the definition, where you can pull out the product twice. An important thing and an important, if you have a group homomorphism, you can look at the image of this thing. You will see in a moment that this is a subgroup. And you can also look at the kernel, which is all the things which are sent to the identity element. This will also be a subgroup. Finally, it turns out it's a normal subgroup. And also we can read off from the kernel whether or not the map is injective, like for vector space. Vector is injective if only if the kernel is 0 or 1, depending on how we count. So definition. So f from G to H, the group homomorphism so the kernel of F is a kernel of F, which is the set of all in G with f of A is equal to 1, where 1 obviously is the unit, the one in H, and the image of F is in F, which is just the set of all image points. The set of all FFA, the A is in G. And so now said we want to say that the kernel of the image are both subgroups, one of G and one of H, and that the kernel V is a normal subgroup. So whatever. It's more a remark. Maybe I will stay for proposition. So let's say f from G to H is a group homomorphism, then the image of f is a subgroup of G. So we should have said that f is from G to H, and the kernel of f is a normal subgroup. And so I've got it wrong, obviously, H of G. Okay, so let's see it. It's directly from this. So here it's directly definition. We have if f of so from f of A, f of B in the image, we get f of AB, which is equal to f of A times is in the image. So that means with any two elements, the product lies in the image, and also f of A, so f of 1, so 1, which is equal to f of 1, lies in the image of f, and f of A to the minus 1, which is, by what I said, f of A to the minus 1, also is in the image of f. And so it's a sum. So here there's nothing we need to check, and the other one is almost as simple. So first we want to see it's a subgroup. So if A and B are in the kernel of f, then it means that f of A is equal to f of B is equal to 1. So thus f of AB is equal to f of A times f of B is equal to 1 times 1 is equal to 1. So AB is in the kernel. And obviously the same with the inverse, f of A to the minus 1 is f. So if so if f of A is equal to 1, if A is in the kernel, then f of A is equal to 1, and so it follows that f of A to the minus 1 is equal to 1 to the minus 1, which is 1. And so A to the minus 1 is in the kernel. And anyway, 1 is, so it's straightforward. Now the normal subgroup. Yeah. So that means we should be able to write GH G to the minus 1. So let H be an element in the kernel of F, and say A be an element in G. Well, in some sense, it's quite easy. See if I take F, A, H, A to the minus 1. Well, this is F of A, F of H, F of A to the minus 1. But this thing is equal to 1 because it's in the kernel, and then this is the inverse of this. So it's kind of for this simple reason that we're here in the kernel, so that this thing doesn't count. And so that means A, H, A to the minus 1 is in the kernel. Okay, so this is quite simple. I also wanted to have to introduce the words I already used about isomorphism and so on. And so projective homomorphism P from G to H is called an isomorphism. Then it's straightforward. Then the inverse map from H to G is also an isomorphism. When we do Algebra theory later, we will very much be interested in automorphisms. So bijective homomorphism, an isomorphism phi from G to itself is called an automorphism. Okay, these are just these words. So let's look just. So in this case, so if there is an isomorphism of phi from G to H, we say G and H are isomorphic, and we write this G isomorphic to H. It's clear from the definition that this is an equivalence relation between groups, and so and as I said, if we just look at the thing as an abstract group, we usually just want to know groups up to isomorphism. So if we can say one group is isomorphic to another, in a suitable sense they are the same. Okay. Let's now I also wanted to write this other thing I stated, namely a group homomorphism phi from G to H is injective if the kernel of consists just of the neutral element, like you're used to it for vector spaces. So this direction is a trivial one. So if clearly phi sends 1 to 1, and if it's injective, it's not allowed to send any other element to 1, and so the kernel has to be just 1. So let's go the other direction. So we assume the kernel of phi is equal to 1. So let A and B be elements in G such that f of A is equal to f of B. We have to show that A is equal to B. Well, in this instance, it should be clear. So then if we take f of A to the minus 1 times B, this is f of A to the minus 1 times f of B, which is equal to 1, because f of A is equal to f of B. So that means that A to the minus 1 B is an element in the kernel of P, which is 1. So if I therefore multiply with a to the minus 1, it follows that a is equal to b. Okay. So that's all, and so therefore f is injective. Other remark or exercise that is quite trivial. So if f m n is a bijection of sets, then the map which I can call maybe f star from the symmetric group, so the set of permutations of M, so the set, so the group of permutations of N, which sends the permutation sigma, so that means the bijection of M to itself. So I take f to the minus 1 composed with sigma composed with f. So I take an element in N, I take its inverse image under f, then I apply this permutation, and then I map it forward. So this map is an isomorphism of groups. Now, obviously, it's the inverse of this. You have to see that this is compatible with multiplication. This is quite clear, and because the multiplication is composition, and if you compose them, then you have f to the minus 1, you have an f here, and f to the minus 1 cancels out, you just compose them. And the inverse of this map is obviously we take the push forward, we take f to the minus 1 stuff. F is a bijective map. Oh, this is f is just a bijection of sets. Then this gives us, then I claim this f lower star is a homomorphism between them, which is an isomorphism. I kind of sketched why, in words why this is true, but you can easily check it. So you have to say it's a homomorphism, so that the group structure here is composition, and you can see if you compose two elements here, this corresponds to the composition here. Okay. And now, one homomorphism that one always, we have defined the factor group of a group by taking the cosets. So you can send every element of the group to the corresponding coset, and the claim is that this map is a group homomorphism. And this is, well, it's not very much of a claim because this is our definition. We say, when we said we have a natural group structure, this just means that we want this to be a homomorphism. So I still call it lemma. So let G be a group. And a normal subgroup. Then P from G, so G mod N, now call it N, yeah, which just sends A to AN, is a surjective group homomorphism. With kernel N. Okay. Well, obviously, that the group homomorphism is clear because if we take P of A times P of B, this by definition is just AN times Pn, which the group structure was just defined as this AEN, which by definition is P of AB. So this is just how we have defined it. And that the kernel is n, if A is an element in the kernel of pi, this is if and only if P of A is a neutral element, which is n. No, the neutral element of the is the coset n. So that means A times n is equal to n, and we see clearly that A times n is equal to n if and only if A is equal to n. A is an element in, and so the kernel of pi is n. So we see, when we come back to this in a moment, but anyway, so we anyway have seen that if we have a group and a normal subgroup, we can always form this factor group. And so you could view this as a way of simplifying your group. So you start with with a certain big complicated group. It has a normal subgroup, then you can take the factor group and you have n, so you can somehow hope to describe G in terms of G mod n and n. So you can try to keep going and describe G in terms of simpler building blocks. And so you cannot make it simpler in this way when G contains no normal subgroup. A group like that is called simple. So group G is simple if the only normal subgroup of G are 1 and G. So, for instance, we have seen that if the number of elements in the group is a P, where P is a prime number, then G is simple. Because in fact we know that the only subgroups are the whole group and 1. It's easy to check. And if I take S3, this is not simple. Because I don't know what I actually wrote it. What I wrote is not written here. Anyway, it's an exercise, but if you just have this the subgroup which contains 1, 2, 3, so the identity, and then the element which sends 1 to 2, 2 to 3, 3 to 1, and the other way around. So 1 to 3, 2 to 1, and 3 to 2. So these, you can easily see that this form a group, and this is a normal subgroup. Okay, and you can check it. I mean, anyway, this would be an exercise. Okay. I can just mention it. I think it's a well-known fact. So there has been this huge project over many years to classify all finite simple groups, which has been brought to some kind of close maybe 10, 20 years ago, and a few thousand pages have been written about it, and you have this kind of thing that there's a certain number of families and 20 exceptional groups, and this is a complete classification of all finite simple groups up to isomorphism, so one actually knows all the basic building blocks of groups. But it's enormously complicated. I think the original proof is about 10,000 pages, and now it's being published in a series of books, maybe in just 3,000 or 4,000 pages. I personally don't think I would be interested, but it's certainly very yeah, it's an interesting statement. Okay. Now, finally, I just wiped it out. We had seen that when we have a normal subgroup, we can make the factor group by this normal subgroup, and we have a homomorphism to it. And now, so we have this map. I should maybe have said that this map phi from G to G mod n, where n is a normal subgroup, is usually called the canonical projection. I want to use these words in the future. By the way, yeah. And now, there is somehow, in some sense, a converse to that. So that means if we have a normal subgroup of a group, we have this quotient group and the canonical projection to it. Now, conversely, if we have this is a surjective homomorphism. If we have a surjective homomorphism from one group to the other, then, in some sense, up to isomorphism, it is the canonical projection. So this group, the image, the group to which it maps, is isomorphic to G modulo normal subgroup, and so this is what I call the homomorphism theorem. I don't know, it has maybe also other names. I call it theorem, although it's quite easy, but we will use it many times. So let phi from G to H be a surjective group homomorphism. And then there exists an isomorphism which I call phi bar from actually there exists a unique isomorphism phi bar from G mod the kernel of phi to H, such that if I take phi bar composed with pi, this is phi. If you like diagrams, we have here G, here we have H, here we have G mod the kernel of phi. This is the projection, and this commutes. Okay, so at any rate, it says that if I have a surjective group homomorphism, we can somehow always just view it as a projection of G to the kernel, or of the G model of the kernel. So it takes almost longer to state than to prove. So we have put this condition here. So what does it say? That, you know, for all elements A in G, we should have phi of A times the kernel of phi. So maybe I write now, I write K to be the kernel of phi. So that A times phi of A times K, phi bar of A times K should be phi of A. Now, you see, what this says, I have prescribed for every element in G mod the kernel, I have described what the image is. So this condition will uniquely determine this map phi bar. The only question is whether it's well defined. So this determines phi bar, because I have said what its image of every element is, you know, to see it is well defined. I should also say that if this definition makes sense, this map phi bar is obviously surjective, because I have said, you know, here every A in the group occurs, so every phi of A also will occur. So if the map is well defined, it's also surjective. So phi bar exists, it is surjective by definition. No, because I just have said, you know, all phi of A occur in the image. So we use this to define phi. So define phi bar of AK equal to phi of A. And so we have to show it's well defined. We can directly show it's well defined. So to show, can directly show it's well defined, it's injective. Phi bar is well defined and injective. So what is this? This is just so we have AK is equal to EK if and only if I take, say, A times B to the minus 1, this is an element in K, which is the kernel of phi. Which is equivalent to saying that phi of A, phi to the minus 1 is equal to 1, phi of A is equal to phi of B. So we say here that these two classes are the same if and only if the image is the same. This says at the same time that it's well defined and that it's injective. So well defined would mean if these are the same, then these are the same, and injective means everyone. So well defined. So thus well defined. And injective, and so it's also bijective, because we have already seen it's surjective. And clearly it is a homomorphism if I take phi bar of AK times PK, this is obviously phi bar A, B, K, which is AB, which is phi of AB, which is phi of A times phi of B, which is phi of AK. So just spell out the definitions. What?
I know.
Yeah. So I spell out the definitions, but not quite the right spelling. Okay, so just one example that we have already seen. So if K is a positive integer, say, or then we have the map R, which we had before, from Z to ZK, which sends a number to the rest when we divide by K. So this is a surjective group homomorphism. And the kernel consists of the elements which are divisible by K. K times Z. So thus we have an isomorphism. CK is isomorphic to Z modulo K times Z. Yeah, so in particular, sometimes we don't need that it's precisely this map, so we always can also have just have also the statement if G to H is a surjective group homomorphism, then H is isomorphic to G modulo the kernel. It is isomorphic via the specific map, but we maybe sometimes don't need. I want to just one more example of a normal subgroup, which we will sometimes use, which is the center of the group. So the center of the group is the set of all elements which commute with all other elements, and this will turn out to be a normal subgroup. So G group, the center of G is the center of G, which is the set of all, we call them A in G, such that AG is equal to GA for all G in G. So the elements which commute with all other elements. And this is a normal subgroup. Because, well, if you conjugate, so because if A is in the center of G, then if I take any element G in G, then G A G to the minus 1 as G and A commute is just A G G to the minus 1 is equal to A. So this is much stronger than a normal subgroup. Conjugating with any element will give me the same element. Good. Okay. So in particular, obviously, if the group is commutative, so clearly G is abelian if and only if G is equal to the center of G. But for instance, if you have a simple group, then its center consists only of the identity element, because otherwise you would have a non-trivial normal subgroup. That can also happen. Okay, so now I want to start talking about group operations, which will is one of the main things that one does with groups, and also how one studies them. So this is somehow related to maybe how originally groups were intended. Groups were originally always thought as groups of symmetry of something. So you have a whatever, if you have a square, you can move it in different ways so that its shape doesn't form. You can turn it, or you can reflect it, and this would be the operator, and it still looks like a square. And so this would be then the action of the group on, say, the square, or maybe just the vertices of the square. And in fact, also when one does, even in Galois 3, the group is somehow, the Galois group is a certain, defined in terms of the action on, for instance, the action on the roots of some equation. And so, now I want to see what it means for a group to act on a set. And I maybe just give related to symmetry, which is to the concept of group operation. So let's first define that. So we have G is a group, and X is a set, and you somehow want to, act with elements in the group on the set. So in some sense, you want to do something like multiply elements in the set with elements in the group, in such a way that it's somehow compatible with the structure of the group. So what does it mean? So an operation or action of G on X is a map, from which are also here just noted by dot, like multiplication group, but it's not quite the same, from G times X to X. So compare Gx I send to the operation of G on X, such that two things hold. It should somehow be compatible with the fact that G is a group. So one thing is that the identity element, so the one in the group, should not do anything, such that if I have 1 times X is equal to X for all X and X. And second, it should be compatible with the product. So we can take the product here in the group, and we can also first act with one element and then on the result with the next. And this should give me the same thing. So that means G, G times H times X is equal to G times H times X. Maybe I don't write the dot here. So here we have the multiplication in the group, and here we have the action. So it looks like the usual associative law, but this happens in different places. So for all X and X and G and H. in G. So this is an action, so it's very simple. For instance, so a trivial example of this is the symmetric group. The symmetric group of order n is defined as the permutations of the set 1 to n. So obviously it acts on the set 1 to n. So for example, is n symmetric group. Order n. So Sn acts on the set 1n, well, basically by its very definition as sigma, which note that Sn is the set of all sigma from 1n to itself, which is bijective. Well, to be right. So therefore, this acts on it by saying sigma acting on x, or maybe we call the number k, is sigma of k. Then clearly, as the multiplication in the group is the composition, so first this makes it an operation. So first, the neutral element in the symmetric group is the one which sends every element to itself, so which is fine. And then you know that sigma times tau, okay, is by definition the composition of these two. So it's just sigma composed with tau, which is just sigma of tau. Which by definition is sigma times tau. Okay. So this is it's so trivial and tautological that it almost looks difficult again. But what?
It's not difficult.
No. Okay, no, I just wanted to. We have some other example. Two, which we will use in the future. They are kind of trivial examples, but they will turn out to be useful. So the G here group. So multiplication in G defines an operation which is called L from G times G to G. So it's an operation of G on itself, which is just done by G H descent. So or maybe I could say G times H is defined to be just the product of G and H. So this is called the left translation in G. So we kind of use this G, multiplying it from the left with the things, and that's why it's called L. And obviously, this is a group. This is an action because in this case the multiplication is the same, and so obviously this is trivially the case. And another case is a conjugation. So again, G is a group.
Is G there fixed element?
What?
We are fixing G here in this it's mapped because we are calling it translation.
Well, no, in the moment we are not fixing it. It's just an action of G on this.
Yeah.
But so for every G we have this, I mean, you could also say it's a left action of G on itself. But anyway, but I just mean this. Later we will actually, in a moment, we will fix the G and see what happens. But no, in the moment we just have, so it's really that G, H is mapped to G times H.
Yeah.
So G is a group again, and we have now an action, the conjugation action from G times G to G, GH is sent to G, H, G to the minus 1. And again, I claim this is an action, because obviously if we take element 1, it does nothing. And if we take, say, if we apply it twice, so we first do G, H, G to the minus 1, and then we apply to this A, H, A to the minus 1. This is the same as if we would do it with the product. So this is AG, H, AG to the minus 1, because the inverse of the product is the product of the inverses the other way around. And so this is also an action. We have some examples of actions of a group on itself. Now, now we can wonder what happens if we have an action and we fix this element in G, like you said, and we want to see what that does. The claim is that if I fix this element and just look at the action via multiplying, acting by this one element on X, this actually becomes a bijective map of X to itself. Okay. Yeah, okay. Yeah. So, the definition. Let G act on a set X. So we have fixed the action, okay? So G X goes to G times X. So the multiplication by G in G is the map. So after I fix the action mg from X to X, which sends the element X to G times X. Clearly, by definition, we have that if we take the identity element, by definition, this is the identity on X, sending every element to itself. And now, as we said, the claim is that this is always a bijection of X to itself. Namely, in fact, that follows directly from the definition for all G in G. We have that mg, if I take, say, mg to the minus 1 and compose it with mg of X, so that means we have G to the minus 1 of times G times X. This is, by the definition, this is G to the minus 1 times G times X. So this is X. So we see And in the same way, we have that mg composed with mg to the minus 1 is also the identity. So thus we see that, so it follows that mg is a bijection with inverse mg to the minus 1. So these are automatically bijections. And so that means I could also say that mg is an element of the symmetric group on X. Oh, this is just so now we want to see that, in fact, the map which sends G to mg is a group homomorphism. This will, if we have the time, bring us to Cayley's theorem, which says that, say, every group or every finite group is a subgroup of a symmetric group, but is isomorphic to a subgroup of say, a symmetric group on letters. What? No, it's arbitrary, but you know, it's not very interesting if the group is infinite, because it's really there's no point for and so. So I will only interest in that case. So, but first, so this lemma. Let G times X makes G group operation. Then the map M from G to the group of permutations of X, which sends G to this thing mg, is a group homomorphism. Obviously, this is also trivial. So if I take something like this, that's also trivial. So let G or H elements in the group and X an element in X. So we just have to see what does it mean. If I take mgh of X, it should be the composition of mg and mh. So this is G times H times X. This is G times H times X. This is mg of mh of X, which is mg times mh of X, because the group structure here is composition. Okay, so it's a group homomorphism. So we want to use this, as I just said, to show that every, so use this to show every, I would only finite group is a subgroup of some symmetric group SE. Okay. Obviously, the proof has nothing to do with finite, but it's I don't think it's any use if the group is infinite. Well, it's just whereas this is the useful result. So this is called Cayley's theorem. So, in fact, every finite group G is But here's isomorphic to homomorphism. Is isomorphic to a subgroup of, I can take the symmetric group on G letters, where G is the number of elements. So we want to use this result in such a way that this map from G to S of G, that this is an injective group homomorphism. It's a group homomorphism, but we need to be injective, and this should be S of G. So that will work. So recall, we had seen it before, that if I take the symmetric group of order G, this is isomorphic to the symmetric group on the set G, because G has the same number of elements, and so they are bijective. So thus, to show G is isomorphic to a subgroup of SG. So now we will want to use this lemma, which is here for any, which says that this you get if you have an action on something, this gives you a map to the symmetric group. For a special action of G on itself, this will give me a map, a homomorphism from G to SG, and we have to do it in such a way that it's injective. Then G will be isomorphic to the image. So we apply the previous lemma. And we apply it to this left translation which we had, L from G times G to G, which was G H maps to G H. So if we now take, so we write, say LG for G and G for the map from G to G, which sends H to G times H, which was what I called MG before. So then we know that the map L from now it's again, I call it again L from G to S of G, which sends G to L of G. This is a group homomorphism. This is what this lemma says. No? The multiplication, which in this case is this left translation by G, is a group homomorphism. And so we only have to show that this map L is injective, then G is isomorphic to its image. Time's up. Which is a subgroup of the symmetric. So assume that G is an element in the kernel of L. So that means that the left translation by G is the identity on G, since every element to itself. So that means G times H is equal to H, or H. in G. So in particular, G times 1 is equal to 1. But G times 1 is equal to G. So then it follows that G is equal to 1. So thus, the kernel of L is equal to 1 and the map is injected. And so that's it. Okay, so therefore we see every finite group is isomorphic to a subgroup of this symmetric group. This is maybe not extremely efficient because after all this thing has as many elements as G obviously, and this has as many elements as G factorial, which is much, much bigger. So we have now found every group inside a much huger one. But still, it's at least one way how one can make every group concrete. So if I have a group with so many elements, I know at least I can put it into this thing. And in fact, this is used in computer algebra to study groups. That there are basically two ways how you kind of study non-commutative groups. Either you view them as groups of matrices, or you view them as permutations. So at least for a computer, this is a sensible way of thinking about groups. Okay, so maybe that's enough for today. Maybe then we'll see each other on Wednesday, I think, and I maybe then will also give you some homework. And you can also, I don't know, if you have any questions, I hope you're not too bored. Or maybe I should now I will end the transmission.